Okay, first I want to apologize. I had a example drafted using BayesiaLab. What happened is work told me I can't share that example. Very sensitive information, and ethics told me because I'm presenting to an international audience, there's issues with it. So I'll come back to my regular research instead of giving a professional application of what I'm doing. So causality, never stay away from causality. I hear that word used several times in the various presentations that I'm in, and I think this is probably one of the most challenging things, especially if you're a data scientist and you're not a subject matter expert yourself on the domain that you're trying to do research in, and you're just saying that this piece of expert information exists somewhere. So that's what I want to talk about today. So I want to go over a primer on causality. How can we produce a better causal model using causal information that we find in an ontology? And I'll provide some background information on observational data sets, algorithms that generate these Bayesian networks that we infer causality from, and how authoritative medical ontologies are really, some of these big ontologies are good sources of causal information that we can mine from. And I'll go over the experiment, which is basically learning two different sets of Bayesian networks and then comparing them. So the introduction to causality, I'm sure a lot of people in this conference are aware of Judeo-Pearl's definition, and I'm not going to read it, but I think it's very nice to have the math and the language and the tools to represent causation. But if we want to learn a Bayesian network and we want it to be effective, right? We have to include prior expertise and clean data. These two things are requirements. But if we want to move into discovery, if we want to discover new relationships or whether or not one model is better than another, then it becomes hard, right? Without having prior expertise that we can trust. And when I say the better, I mean in terms of predictive accuracy of a model, and also better in terms of representing reality. So what is your model in congruence with? We're talking about expert knowledge. Are we talking about one expert, a group of experts, or in the case of an ontology, the collective expertise of hundreds and thousands of people? So inferring causality is not the same as establishing causality. We can infer causality from a learned model, the BayesiaLab chapter 3. I think you guys actually have a pretty good documentation there. But if we want to establish causality between two variables, we're going to need a couple more things, right? So association, correlation, we all know that the correlation is not causation. We learned that from Stat 101. But what else we need, I think Dr. Rubin mentioned this, is we need sequencing of the data variables because the cause always precedes the effect. We need our counterfactuals, the what-if scenarios. We deal with confounding, which has been mentioned several times. And we also need a causal mechanism, which is the process creating a causal relationship, and contextual evidence, which are causal details external to the data. So the first 3 or 4 points on here, you can do that with the data. The last 2 or 3 on here, you can't do with just data alone. You're going to need some extra knowledge to be able to confirm this. So a model based on data will provide insight into confounding variables outside of data, or pre-existing causal mechanisms, or incorporating any contextual evidence. So data alone will not do that. But Bayesian networks learn from observational patient data can be used for causal inference, and we do that a lot, but they don't incorporate any prior knowledge that establishes a causal relationship. So the claim that I'm making is that you don't need to be a subject matter expert or know a subject matter expert to produce these priors. We can get these from ontologies that exist within a domain. So experiment, right? I'm getting some prior knowledge directions from ontology, and we're going to modify it. And then we're going to compare the baseline to the modified in terms of agreement of arcs. We're going to do a AROC curve for predictive accuracy. And then we're also going to see its predictive accuracy for a single node. And then we're going to cross validate the predictive accuracy of that node. So for the observational data set, I really appreciate Dr. Rubin coming on before me, because a third of my experiments was actually on the study data set, and causality and mental health is very interesting to me because there's no way to stick a probe in somebody's head during the process to see if a drug works or not. So we're relying on observational data. So here I'm using real data from the NACC. And the node that we're going to try and predict is whether or not the model that we're creating is useful for predicting dementia. And also, this is good because we already know that dementia is a symptom that comes after Alzheimer's. The algorithm I'm using will be MMHC. I'm not going to read this. There's only so many algorithms you can use to learn a Bayesian network, a directed Bayesian network. And an authoritative medical ontology. So this term essentially applies to any ontology that has been thoroughly vetted by many people. So I'm talking about ICD-10, SNOMED, there's a gene ontology. There's just these ontologies out there that are incredibly robust. And to be able to get causal information, established causal information from them. So the first step to doing this is to graph the symptoms that we're getting from the data. And we're grafting this essentially onto ICD-10, or what I've done is graph this onto ICD-10. You can graph it onto any ontology. But this is really the start of the exploration process, because what you're seeing here is that the symptoms that we're getting from the data set is not representative of everything that we know about Alzheimer's. And the same is true with STAR-D. It's not representative of everything that's been diagnosed or we're capable of diagnosing using the ICD-10 ontology. So by doing this, we're seeing what other symptoms could potentially be external to the model that we're generating. SNOMED is actually very nice in the sense that it has explicit relationship types that gives us this causal information, right? The example I'm using here is actually good. I thought I made a mistake, but this is actually good because this is actually a STAR-D example. So right here, it's saying that the causative agent for hypersomnia is alcohol. So alcohol abuse and hypersomnia are symptoms within STAR-D. So the way that these two symptoms are diagnosed is that one precedes the other, but also one is the cause of the other. So when a doctor diagnoses the symptom, it's not in reverse, right? So the question is, or the assumption is that you have hypersomnia because you're abusing alcohol, and not the reverse. So this is what I'm searching for in each of these ontologies, these three different findings, or these three different relationship types. So the qualitative clinical information also exists in certain browsers. So here's an ICD-10 CM browser that's giving us qualitative information for how these symptoms work. And as not a clinician, as a non-clinician, I can take a look at this and I can say, okay, dementia causes progressive decline in language, dementia causes progressive decline in memory and executive judgment. So these are all causal mechanisms for the disease progression in terms of Alzheimer's. And this is what we want to work into our model. Subsumption, not going to go too much into this, but really it's the way that the ontology is structured. This is not always causal, but it is associative. So creating a baseline. So very quickly, this is pretty simple to do. Just do this, and I really wish I had BayesiaLab, because then you can isolate the nodes. But I would always say that the network that you're seeing on the right here is, and the strength of the relationships that's learned from the data is inconsequential. The question here is not whether or not these relationships exist. They do if you want to fall back on just look at the data and what it says. The question really here is that using these algorithms, which is pretty much all we know on how to learn a Bayesian network from the data, can we produce a better model than what this hill climbing or the maximum restrictive hill climbing can do? That's the question, and it's very hard to actually produce a better model than what our algorithms are capable of. This is what we want to plug into the model, so we know that these are established causal relationships related to Alzheimer's disease. So the one that I want to draw your attention to, it's actually to the third to last one here, which is ALS, Lou Gehrig's disease, and whether or not somebody falls, right? So as Lou Gehrig's disease developed, you also develop muscle issues. And so as your leg muscles weaken, right, this leads to having additional falls and getting hurt and all this. So if we go back to this model here that I'm learning just by using the algorithm, you'll see that the node is actually excluded from being a part of the network. The question is, okay, is that related? Number one, is it related? And two, if we already know that there's some kind of established cause within an ontology, once I incorporate that knowledge into the model, does that bring that node back into the fold? What else does research say specifically about what's going on here with that node? Okay, so these are the pairs, right? I'm going to go over them. This is what we found in the ontology, and we can also confirm these with additional research that's out there as well. So we want to consider these ordered variable pairs. We want to do that during the greedy hill climbing phase of the algorithm to produce a modified network. And what I'm doing here is I'm blacklisting the reverse. So I'm not forcing these relationships into the model. They may or may not exist. I want the algorithm to have the freedom to choose if it exists or not. But I do want to blacklist the reverse, right? So I don't want falling to be the cause of Lou Gehrig's disease. So even though I'm not a clinician, logically that makes sense. So here is the comparison of the modified network versus the original. I have to try and read this, but what I'm trying to show here is that the ALS node does get reincorporated into the network. And this is based on the learning and not because I'm forcing it. So comparing the baseline versus the modified network, right here what I'm doing is the level of arc agreement, or what's in the original versus the modified, is about 87%. We get 6 new relationships and we remove 8 false, or false negative means we remove 8 relationships. And if we are setting the node of prediction to demented, the new model does predict that node markedly better than our old model. And here we're looking at the AROC curves, so the 95th confidence interval. For the baseline one, we're just using the algorithm that's between 9.38 and 9.58, and if you're using the modified, it's between 9.52 and 9.66. Small overlap in there, but the confidence interval almost breaks free completely. And keeping in mind, this is the modified network against an algorithm that we consider to be the best that we have. And on the bottom here, I use a less sophisticated algorithm, so just regular hill climb, and it does better in that too. So it actually is able to constrict a less accurate model and make it more accurate. So taking a closer look at the relationships that are added, I won't go through all of them, but really it's the second to last one, right? And there are citations out there that suggest that this is true. But also the way that the disease progresses, these symptoms are collected early on until the patient is no longer able to provide useful data, right? So if you think about Alzheimer's, it's very interesting in the beginning and end phase. So it progresses at different rates for everyone. So the duration between symptoms no longer matter when you perform the analysis. It all has to do with whether or not certain things are observed temporally within that sequence. So within that development, right? So Lou Gehrig's disease, you get that. You probably get the diagnosis of a fall, right? There's potential of getting that before the fall, but it's the causative establishment there is never that. So in conclusion, causal knowledge and mechanisms contained in these ontologies can be used to orient the arcs in a causal Bayesian network. It's learned from data. A model with prior knowledge provides a better representation of the complexities of disease. So we all know this if we accept what's in the ontology. And my argument, right, is really I can't be an SME in every domain that I look for. Right now, we're trying to apply this in the purchasing patterns of government, right, and our security and protection equipment. And it works for that too, as long as the taxonomy is robust enough and that the causal mechanisms are properly documented. So the constraints reach congruence between the model and the ontological causal claim. And this is important because that ontological causal claim represents one of the best understandings that I believe to be of that disease, because it's the way that that disease or that symptom is able to be diagnosed. It's how our billing system works. So the moment that the money becomes, then we know we have something. So modified CBNs with a better predictive accuracy compared to the baselines when we do the AROC curves. And finally, we have this is a new methodology for gathering and using ontological knowledge as a prior. So that is it for me.